Okay, good morning. So today we will talk about the ring of polynomials. Ring of polynomials, and that will be probably the most important example of a ring for the next few lectures. Actually, in my lecture, I will do exposition in slightly more general version than the textbook, because we can just talk about the ring of formal power series from the very beginning. So you will see that formulas and the proofs are essentially identical, but we get a slightly more general result. Okay, so let's start with our first definition for today. That's definition 1. Let's define the ring of formal power series. Okay, so the first part of this definition would be the following. So let R be a ring. Then we say that a formal power series f of x with coefficients in R is an infinite formal sum, written as follows. So f of x so this is formal sum, and I will use the red for this capital sigma to distinguish it from the actual sum. Okay, so this is an infinite formal sum of the following form: ai x to the I. So in other words, we can also write that this is a0 plus a1x plus a2x squared, etc. Okay, so note that this expression, is not an actual sum. Is not an actual sum. Well, at least for now. But rather just a way to write a sequence of coefficients. Sequence of coefficients ai, parameterized by natural numbers. Okay. So, and oh, I forgot to write the last part, where, of course, all this ai belong to R for all I being natural number. Okay. Now, a particular case of the formal power series power series for which almost all coefficients are 0 except for finitely many, except for finitely many, is called a polynomial. For finitely many i's is called a polynomial. So the polynomial is just a formal power series for which this ai's are 0, starting from large enough number. Okay, so and in this case, when only finitely many of ai's is non-zero, we say that the largest n, for which a sub n is non-zero is called a degree of polynomial. It's called a degree of polynomial. Here probably we should say when exists, because there is a silly case of a polynomial which is 0, where all coefficients are 0. We don't talk about the degree of that. So we define the degree only for non-zero polynomial. Okay, so far this is just kind of convention to write sequences, right? No more than that. So we defined a polynomial just as a formal power series, just as a sophisticated way of writing the sequence of coefficients. So the next thing we are going to do is we will define the addition and multiplication of formal power series. Addition and multiplication of formal power series. Okay, so let f and g be two formal power series. A0 plus a1x plus a2x squared, 2x squared, etc. And same for g of x, which will be b0, b1x, b2x squared, etc. And of course, this ai, bi, they will belong to some ring R. B formal power series. Then we define, and we define. Okay, so the sum of the two is simply the formal power series for which we added the coefficients. So for the constant term, we'll just add a0, b0. For the next term, we'll just add a1, b1, a2, b2, pretty much as you would add the sequences, right? So in other words, this whole thing is the formal power series. So we get this formal sum from j equals 0 to plus infinity with coefficients cj, where this cj is nothing as aj plus bj. Okay, so now the multiplication is actually much more interesting. So let's define the multiplication of two formal power series as, again, the formal power series. Formal power series with coefficients in R, which we will denote as d sub j. And as d sub j are computed from the coefficients of the original series as follows. So that will be a sum from 0 0 to j of ai multiplied by b j minus I. Now, this is an actual sum. This is an actual sum of elements in R. Okay, so and here it comes the theorem. Here it comes the theorem that formal power series actually form a ring with respect to these two binary operations. So that will be our theorem 1. No. Power series form a ring. Well, of course, with respect to the above operations plus and dot. And this ring is denoted as R double square brackets X. Okay, so the way how the proof goes, by the way, any questions so far about the formulation of the theorem? Okay, so for the proof, the first thing to note is that almost immediately we get that R of X with a binary operation plus is an abelian group. Abelian group. Similarly to how the sequences form an abelian group, right? Sequences in R. Similarly to how sequences in R form an abelian group. So the identity of this abelian group is the zero sequence, and you add component twice and take the inverses component twice. Okay, so the interesting part is actually to prove that the multiplication operation from R of X cross R of X to the ring of formal power series in R is associative. So now I will reproduce this ugly long calculation from the textbook, but I will stress which parts where we actually have the formal sums and where we have the actual sums. So this is to my taste, this is rather important part. Okay, so let's take one formal power series with coefficients ai, and let's multiply it by another formal power series with coefficients bj. So our goal is to prove that if we first use the formula for the multiplication of formal power series for these two guys, actually let's put each of them in the round brackets. So let's first multiply this two, and then multiply it by another formal power series with coefficients ck. ck, xk. Okay, so our goal is to prove is that this is the same as first multiplying second and third power series followed by multiplication on the left by the first formal power series. And what happens then is we just kind of apply the definition of multiplication for the first guy. So what we will get is the formal power series, and let's say that the index of summation here is n runs from 0 to plus infinity, for which the coefficients are an actual sum from 0 to n, ai b sub n minus I. And those are coefficients in front of x to the n. So note that this black sum is an actual sum in R. Okay, and then we multiply it by the benefits of the online Blackboard is that I can do this. Here we go. Okay, so what do we get? What do we get next? Then we kind of use the multiplication rule to multiply the rest. And what we will get is the sum from s equals 0 to plus infinity. So we get the formal power series, and the coefficients of that formal power series are computed as follows. So they are computed as double sum n equals 0 to s of the sum I equals 0 to n ai b to the n minus I multiplied by c to the s minus n. And that's a coefficient in front of x to the s. Okay. Nope. So note that this calculation is actually, this is calculation in R. Calculation in R. Okay, so the last thing to note is that this is actually the formal power series s equals 0 to plus infinity. S equals 0 to plus infinity, and the coefficients there are nothing as the sum over all ijk, which add up to s and are greater than 0. Greater than 0, j greater than 0, k greater than 0. ai, bj, ck, ck, and that's the coefficient in front of x to the s. And this is literally what will happen if you take this first expression, and compute the product in a different, for the different kind of for the different order. Sorry. X to the s. So let's erase these brackets and let's put them in a different place. Here we go. Okay, so in both cases, you'll get the same sum. Okay, similarly to what I did right now, one can prove the right and left distributive laws. So I won't write this down, of course. Right and left distributive laws. Derivative laws hold in the ring of formal power series. Well, so we can talk about the ring of formal power series. Proof by similar calculation. Okay, so this concludes the proof of our first theorem. So now we have a ring of formal power series. And do you have any questions so far about the theorem or its proof? Okay, so now let's talk about the main application of this theorem. And main for us, main application of this theorem will be proposition 1. So that polynomials form the set of polynomials. Actually, let's just polynomials form a subring. Form a subring, which is denoted by R with a single square bracket X of the ring of formal power series. Of the ring of formal power series. Well, and in order to prove that some subset is a subring, we need to prove that it is an abelian group. It is closed, and it is closed with respect to multiplication. So we need to show that R of X plus is an abelian group. And that R of X is closed with respect to multiplication of formal power series. Multiplication of formal power series. Okay, well, indeed, kind of zero sequence did some 0x to the I equals 0 to plus infinity is a polynomial. Now, if f of x some 0 to n an xn is a polynomial, and g of x sum from j equals 0 to n bn xn is a bm. So this will be a polynomial of degree. The first one will be a polynomial of degree n, the second one of degree n is a polynomial of degree m. And then from here it follows that minus f of x and minus f of x is a polynomial of degree n, polynomial of degree n, and f of x plus g of x, the g of x is a polynomial of degree at most maximum, the m and n, most maximum m and n. Okay. And of course, the product of f of x and g of x, x and g of x, is a polynomial of degree at most m times n. Now you might ask, why do I want to say that at most in the last part? And that's because I never put any restrictions on the ring R. In particular, the ring R might have 0 divisors. Okay, so let's go ahead and consider a couple examples. So let's do example 1. Let R be the ring of integers modulo 6, this is 6, and consider the ring of polynomials. The ring of polynomials. The ring of polynomials Z6. Oh, Z6 of X. Okay, so let's take two elements. Let's take two elements. Say f of x would be 3x plus 2. And Z6 of x. And let's take g of x, which would be 2x plus 3. And Z6 of x. And let's multiply the two. So f of x, g of x, 3x plus 2, 2x plus 3. So the formula for the multiplication of this kind of truncated formal power series, of course, would give pretty much what you expect. It would give that this is 6x squared plus 13x plus 6. Now, because this is 0 in Z6, and this is 0 in Z6, what we get is that the product of these two polynomials is just x. So we take two polynomials of degree 2, we multiply them out, we got a polynomial of degree 1. Okay, so this is what can happen when our ground ring R has 0 divisors. So kind of the leading term canceled here. Okay, so even better, the polynomials can have inverses in the ring of polynomials sometime. So let's look at example 2. So here, let's consider a ring of polynomials over Z4. And let's multiply the polynomial 2x plus 1 by itself. 2x plus 1. So what we get is, we'll find that this is 4x squared plus 4x plus 1. So in other words, 2x plus 1 has multiplicative inverse in Z4 of x. Okay. Now the last kind of thing, the last example I want to consider right now. Kind of the last remark. Probably let me just say that this is a remark. Note that in general, the polynomial is not oh, sorry about that. I'll just talk about this remark when we will come to the evaluation homomorphism. It will just naturally fit there. What I want to say is that different polynomials might always take the same value when they evaluate it. R, but I forgot that I haven't yet defined the evaluation. Okay. So, any questions about the example so far? Before we proceed to the polynomials in several variables. Okay, so now our idea of the ring of polynomials can be continued. All variables. So recall that we kind of started with an arbitrary ring R, and we defined a ring of polynomials with coefficients in R. So kind of, but what if we start with a ring of polynomials in the first place? Then if we'll consider polynomials with coefficients in the ring of polynomials, what we'll get is polynomial in several variables. Okay, so let's start with proposition 2. So let R be a ring. Let R be a ring. Then if we take polynomials in R with in X with coefficients in R, and then take polynomials in Y with the coefficients in the resulting ring. That will be isomorphic to the following ring. If we first look at the polynomials in Y with coefficients in R, and then consider polynomials in X with coefficients in this kind of R prime. So let's say that this is R prime, and this is R double prime. Okay, and they are isomorphic as rings. So I will leave the proof as homework. Proof left as homework. Again, there is no big secret here. You just kind of see that the multiplication and the two, you just establish a bijection between the two rings and see that it is a ring homomorphism. Okay, and this motivates the following definition. This allows one to introduce definition 2. Now, if we look at for ring R, for a ring R, we define R the ring of polynomials in several indeterminates, x1 to xn, as simply starting with the ring of polynomials in x1, then using this as a ground ring to construct a ring of polynomials in x2 with coefficients in that, and so on. x3. All the way to xn. And again, the order doesn't matter precisely because of proposition 2. The order of x1, xn doesn't matter by proposition 2. Okay. Okay, so we kind of seen on the previous slide that when R have 0 divisors, then in the ring of polynomials over R, weird thing can happen. But it turns out that if our original ring R had no 0 divisors, and for example had a unity, then this property would be shared by the ring of polynomials. So our next kind of proposition would be the following. And that will be proposition. Wait a second. You have proposition 2 already. Yeah. So that will be proposition 3. Now let D be an integral domain. Let D be an integral domain, not just an arbitrary ring. So this will be a commutative ring with unity and no 0 divisors, like the best ring you can imagine. Then the ring of polynomials in X is also an integral domain. Yes, also an integral domain. Again, I will leave the proof of this as the homework exercise. Left as homework. I'll just give a short sketch. Need to show that there is a unity in d of x. That it is commutative, but it is obvious kind of it is a unity in d of x, and that multiplication of two non-zero zero polynomials can be zero. Cannot be zero. Okay, so that's that's kind of neat. And in light of the previous slide, we immediately get a corollary. I immediately get the corollary that if D is an integral domain, D is an integral domain, then so is D, the ring of polynomials in several variables over D. So we immediately get that it cannot have zero divisors. Well, when we have an integral domain, last time we have defined the field of quotients for an integral domain. So the field of quotients of this ring of polynomials let me actually put this on the blackboard. Call that last time we associated field of fractions to every integral domain. This allows for the following definition. Now that will be definition 3. So let D be an integral domain then the field of quotients. Oh, sorry. We said that this is the field of quotients. So these two notions are synonyms, so I will use them interchangeably. Sorry about that. The field of quotients of D x1 to xn of the ring of polynomials in several variables over D is called the field of rational functions. The field of rational functions in x1 then over D. And it is denoted by D with round brackets, x1 to xn. So we had today we introduced two rings associated to any ring. That's the ring of polynomials, that is the ring of formal power series, and the ring of polynomials. But when we have an integral domain, we can actually consider the field of rational functions over D. Okay. So any questions so far? So we talked a lot about now the standard the standard rings we can associate to R or D, like the ring of polynomials, the ring of formal power series, the field of rational functions. Now let's talk about some properties of the ring of polynomials, which are very specific to the ring of polynomials. And let's talk about evaluation homomorphisms. Homomorphism. And what's so important actually about the polynomials, not just the formal power series or rational functions. Okay, so let's recall our example of a ring. Call that in general, if X is a set and R is a ring, then the collection of all functions from X to R is a ring on its own. Okay, is a ring on its own, and moreover, for every element a small in X, we can define an evaluation homomorphism. Evaluation homomorphism, let's say that this is psi of A, which will be a function from the ring of functions to the ring R. We just take a function f of x, and sends it to the value of this function f of A. So we talked about this when we first introduced the basic of the basic examples of a ring. So we actually have the following theorem that if we have a polynomial, so that will be theorem 2, I believe. that if we have a polynomial over a field, so for simplicity, for the next of the lecture, we will always assume that we work with polynomials over a field. Much of this relates to an integral domain, but this kind of will simplify our life a lot. So for the theorem 2, let f and e be fields. F and e be fields. And let's suppose that f is a subfield of e. And for any element, alpha in the field E, one can define a map which I will denote as phi sub alpha from the ring of polynomials in X over the field F to the field E as follows. So we take F alpha, and remember that kind of the polynomial is a formal power series where only finitely many coefficients are non-zero, right? And let's define the phi of alpha as nothing as just the sum of a0 plus a1 alpha plus a2 alpha squared plus an alpha n. So note that this calculation is in E. This calculation is in E. Okay. So then the statement of this theorem says that this map is a ring homomorphism. This map is a ring homomorphism. This map is a ring homomorphism called evaluation at alpha. Called evaluation at alpha. So, and of course we denote f alpha applied to polynomial f of x simply as f of alpha. Okay, so sketch of the proof would go as follows. Of course, by now you have seen many proofs of very similar type. So we have to check that f alpha applied to the sum of the two polynomials, f of x and g of x plus g of x is nothing as f alpha applied to f of x and plus the result of f alpha applied to g of x, and same for multiplication. Alpha of f of x multiplied by the g of x is also just the multiplication of the results of evaluation. Alpha of g of x. Now both of course are just obtained by straightforward calculation. Both are proved by direct computation. Direct. Okay. Now, kind of an important thing here, the moral of the story. Moral: with every polynomial f of x in R, we used polynomials over a field already, so that was a field F. We can associate a function which by abuse of notation is also denoted by the symbol f, function f from the field, so that was the field E, field E to E, and the value of this function kind of sends alpha to f of alpha. Now here's an important point. Here's an important point. Different polynomials might define the same function. And let's look at example 3. So consider the ring of polynomials over Z2. Right? Z2 is a field, so everything is good here. And let's take two polynomials. Let's take two polynomials, f of x being x and g of x equals to x cubed, are different polynomials. Yet f of 0 equals to 0 equals to g of 0, and f of 1 equals to 1 equals to g of 1. So f, g, so the associated functions are the same. They define same function. Can I scroll it a little bit? Yeah, sorry for running out of space on this slide. So that's important thing to keep in mind, that remember how we defined polynomials. We define them as sequences which kind of which are truncated, such that as a sequence of coefficients which becomes 0 starting from some point. So in light of this definition, x and x cubed are different polynomials in Z2 of x. Yet if we evaluate them on every single element of our field, we always get the same result. So, okay. Now let's talk a little bit kind of put some simple remarks that if we take evaluation of a constant polynomial a0 at any alpha, we always get a0. That if we take evaluation of a polynomial a1 times x, we get a1 times alpha, and that's in E. That's in E. And another remark is, what's so special about polynomials? Mark 2. Note that in the first part of the lecture, we also defined formal power series and rational functions. Power series and rational functions. So both are well defined as rings. Both are well defined as rings, but there is no evaluation homomorphism. No evaluation homomorphism. So if we want evaluation homomorphism, if we want to associate a function, we need to restrict ourselves to the polynomials. If we want to get this function on the entire field, of course, you kind of know that for the rational function, you can define partially defined functions and so on. We're not going to go in this technicality, but that's this remark too kind of explains why we really need to restrict our attention to the ring of polynomials, not just formal power series or rational functions for now. Okay. So out of this discussion about the evaluation homomorphism, we arrive at the definition. That's probably definition 4. So I kind of, yeah, that's definition 4. Definition 4 of a zero of polynomials. Of a zero of a polynomial. So let f be a subfield of E. Well, it can be, f and E can be equal to each other. That's, by the way, relates to the previous theorem, of course. I probably wrote it. Yeah. So f is a subfield of E, but of course it can be equal to E. B fields. And alpha be an element of a field E. Then let's look at the evaluation homomorphism of alpha, right? It sends polynomials over f to E, just evaluating them at this point. So we say this is an evaluation homomorphism, is an evaluation homomorphism. Then we say that alpha is a zero of polynomial f of x. alpha is 0 of a polynomial f of x in this ring of polynomials over f if the evaluation of f of x at alpha, as you might guess, is 0, which we also denote as simply f of alpha. Okay. Now, of course, you kind of know that if polynomial have a 0, the usual polynomial have a 0, then we can factorize it. So we can basically divide it by some linear polynomial, presented as a product of some linear polynomial and a polynomial of a smaller degree. When we talk about polynomials over real or complex numbers. And of course, this generalizes to an arbitrary field. So the last topic, which we will start today, will deal about the factorization of polynomials over a field. And we will talk, of course, more about this on the next lecture, but today we will just set up the basic notions of polynomials over a field. And our main theorem here would be the division algorithm for polynomials. I lost track of numbers, so I know what number of the theorem it is. So it will be the division algorithm for f of x. Okay, and the theorem is stated as follows. So let f of x, g of x be the two polynomials, such that the degree of f of x equals to n, and degree of g of x is some m, and we assume that g of x is not zero. G of x is not zero. So actually there is no need to assume that f of x is non-zero. Just remember that you have to, this is kind of annoying, but you have to always talk about the zero polynomial separately when you talk about the degree. Okay, so then the statement of the theorem is that, and there exists a unique pair of polynomials, q of x and r of x, which stands for the quotient and the remainder of the division, of course, such that, first of all, f of x can be written as q of x multiplied by the g of x plus the remainder term, r of x. And second of all, that the degree of r of x is strictly less than the degree of g of x. Or equivalent, or just remainder can be also 0. Okay, so as far as how the proof goes, so first let's prove uniqueness. Oh, so first let's prove existence. So consider the set. Let's say it will be S. And this will be a set of the following expressions of f of x minus g of x times s of x, where s of x is just some polynomial in our polynomial ring over f. So this is an infinite crazy set of polynomials. However, it must have the element of the smallest degree. Consider the set. It must have the element of the smallest degree. And to see that, recall that, well, obviously S is non-empty, right? And degree of every polynomial, I don't know, P of X, degree of every polynomial is a natural number, right? For every non-zero polynomial. So of course there is kind of, there is the polynomial which has the smallest degree in this set. Okay, smallest degree, and let's say that this polynomial is R of X. Okay, so then this R of X is the following polynomial. It's just, suppose it has degree K, right? Let's call it degree K. It'll be CKXK plus all the way plus C0, where K is strictly less than the degree of G of X. Okay, so what do we have is that this R of X is f of X minus G of X times S of X. Oh, let me actually comment why K is strictly less than the degree of G of X, because otherwise we can change S, we can change S to something like S2 of X equals to S1 of X plus Cm over Bm, where G of X is B0 plus Bm x to the m. So you can basically cancel. Yes.
Can you repeat how did we change? We can change x.
Oh yeah. Thanks. Let me actually. Yeah. Sorry. I was trying to swipe this under the rug, but that's not a good idea. Let's just write everything down carefully. Okay. So let's forget about this. So we assume that there is an element of the smallest degree. and we call this element r of x. So now the claim is that the degree of r of x is strictly smaller than the degree of g of x. Degree of g of x. Indeed. Assume the opposite. That degree of s of x greater or equal than the degree of r of x. R of x is greater or equal than the degree of g of x. Okay, so let g of x be the following guy. So g of x will be the polynomial of degree m, b0 plus all the way to bm xm. So, and now take s prime of x, r prime. Now take, let's take and suppose that the r of x kind of realized as f of x minus g of x times s1 of x. Now let's take s2 of x to be the same as 1 of x, but just add something to cancel the leading term of r of x. To cancel the leading term of r of x, and that will be cm over bm. Then what do we have? Then we have that r2 of x equals to f of x minus g of x s2 of x. S2 of x, right? This is f of x minus g of x s1 of x minus this cm over bm g of x. So this thing here is r of x, right? R of x, which equal to ck x to the k plus etc plus c0. And here we can kind of cm over bm, and that was plus all the way to the c k x to the k minus m. Yeah, this is plus c k x to the k minus m divided by e multiplied by gx. And what you will find here is that for this r2, oh, sorry. That's what happens when you improvise. Let's just do this. Then what happens is that the leading term cancels. So you would get ck x to the k plus whatever. We don't really care what happens for the subleading terms. C0 minus ck over bm x to the k minus m multiplied by the bm xm plus etc. So from here it follows that the degree of R2 is strictly less than the degree of R1. And here we come to the contradiction that the degree of R is minimal. We come to contradiction that degree of R is minimal. R is minimal. Here we go. Okay, sorry about that. Now I won't prove the uniqueness because I'm out of time, but I will remind this theorem next time, and now I will be glad to answer your questions. And as usual, I will restart the session and continue with the office hours.